In this video, we're going to talk about when to select which strategy for integration. Last term, when we were doing differentiation, it was pretty straightforward. You could look at the function and you could tell, aha, I have an e to the x, so I need to do e to the x as the derivative, or I need to do chain rule because I have the composition of functions. And as we've seen, integration is much, much more challenging. In this video, we aren't going to cover any new material. You aren't going to learn any new techniques. We're just going to break down when would you want to choose which technique and spend the time doing a little bit more practice. And I feel like it's helpful to sort of go through this mental checklist. The first check is you're given an integral and you have to ask yourself, can it be rewritten or simplified? So for example, if I were given a function like the integral of x to the fourth times x squared minus 3 dx. This is a classic example of something that I can't apply power rule directly because these are two different factors multiplied by one another. But if I were to just use the distributive property and get x to the sixth minus 3x to the fourth dx, now I can apply power rule on each of these terms individually. So that's one thing to keep in mind. The next thing is to say, is it on the table? Meaning, there's a set number of sort of integral facts that are important to keep track of, and I printed out a table mysteriously that was found somewhere. Can we read all of this at once? Here, take a screenshot of that, or you can look it up on an ebook. Some of these, it looks like a lot, right? But some of these are things that we already know. This is just power rule, that I raise the power and divide by that power. This focus isn't so great. Let's see if that's better. There we go, that looks better. Okay. The derivative of 1 over x is natural log of x. This one right here is one that I don't think that you need to memorize. So I'm crossing it out. We already know the integral of sine, the integral of cosine, the integral of secant squared. These are all just our derivative facts from last term. These down here are ones that I can convince you that we can figure out if we need to figure out just by using u substitution and being clever. We aren't going to use sinh or cosh. And these natural log ones are ones that come directly from using trig substitutions, so we know those. So I've narrowed the list quite a bit, and I claim that some of them are ones that you can use substitutions for. So that's my next technique, right? Look at the table. And if it's not on the table, does a u substitution jump out? That's one of our go-to techniques. In order to use a u substitution, you need to make sure that you have a composition of functions, so a function within a function. And the derivative of the inside function is somehow available. Meaning, a classic example of something like this would be like 1 over the square root of x to the third plus 4 all times x squared dx. Why is this a classic example? Because it's a composition of functions that I have this crazy function within the function. It's all raised to the negative 1/2 power. And the inside function, if I let u equal x cubed plus 4, I have the derivative sitting right here. I just have to multiply by 3. So this is an example of a u substitution that just jumps out. Does a trig substitution jump out? And these are going to be of the form something like this, or a variation from the section that we saw before. Does pi parts jump out? For pi parts, we need to have a product where the v du is easy to integrate. So lots of these have products, but we need to make sure that when we actually set up the by parts, that whatever the parts are going to be something that we actually know how to deal with. And finally, partial fractions I think is the easiest technique to recognize, because it's always a rational function. You have a polynomial on top and you have a polynomial on bottom. So these are all the different techniques that we've looked at and the different strategies. And now I'm just going to do a couple of examples. Let's look at this example in particular. We see that there are some trig pieces, And this is an example of something that I don't think that you need to memorize because we can actually figure out what to do. This is one of the identities on our table, in fact. So we know what the answer is from this table, but let's take a look at if we can figure it out without using a table. My first thought is that I like dealing with sines and cosines better than cosecants and cotangents. So I'm just going to convert this into what this is in terms of our basic trig identities. So cosecant x is the same thing as 1 over sine x. And cotangent x is the reciprocal of tangent. So instead of sine over cosine, it's going to be cosine over sine. I haven't done any integration. There's no calculus here. I'm just converting these into their basic pieces and rewriting it. Now when I rewrite it, I have a cosine x in the numerator, and I have a sine squared x in the denominator. And looking at this, now I think we can go back to our chapter on trig substitutions, but this is a pretty straightforward u substitution. That if I were to let u equal sine of x, then du is hiding right there. It's the cosine x dx. And I can convert this whole big messy thing as just the integral of the cosine x and dx become my du. And on the denominator, I get a u squared. And if I integrate, this is actually, maybe I'll rewrite this. This is the integral of u to the negative 2 du. So this is just u to the negative 1 times the reciprocal of negative 1, which is negative 1, plus b, which is just, what was my u in this case? U was sine of x, so this is negative sine of x all raised to the negative 1 power. Or I could rewrite that as negative 1 divided by sine of x. That's what it means to be raised to the negative 1 power. It's the multiplicative reciprocal. Or, as the book writes it, this is negative cosecant of x. So we did have to do a little bit of work, but we can figure out, we simplified some things and then did a u substitution for this particular technique. Let's look at another example and think about how are we going to set this one up. So I think to myself, is there anything that I can simplify? Not exactly. I could use some sort of double angle identity, but I think that might just make it messier. This is a classic example of what I would say is a by parts example, that I have this part and I have this part, and e to the x is something that's really easy to both take derivatives of and integrate, that it always stays as e to the x. So I would just try thinking about my u part being equal to sine of 2x, because then du is just going to be 2 cosine 2x using chain rule. The derivative of sine is cosine and the derivative of 2x is 2. My dv is equal to e to the x, 2x dx. And then my b is going to be equal to the antiderivative of e to the x, which is still just e to the x. And without going through all of the pieces of this, that means that this integral is going to be equal to uv, which is sine of 2x times e to the x, minus the integral of b du, minus the integral of 2 cosine 2x e dx dx. And you say to me, well, Carolyn, this doesn't look like it's gotten any easier, right? That we're sort of back at where we started. And I say, well, do not despair. We will do one more step of this, and then everything will become clear. So let's do this one more time. I'm going to factor out the 2 so that we don't have to deal with it. And we're going to do by parts again. Again, letting u equal cosine of 2x. Maybe I'll put the 2 here. Cosine of 2 cosine 2x. So then du would be equal to negative 4 sine of 2x. dv is equal to e to the x. v is equal to e to the x. And we do by parts again. just for this piece of the integral. So we still have this leading term, sine of 2x e to the x minus uv 2 cosine 2x e to the x minus the integral of v du. So this minus the negative becomes positive 4 sine 2x e to the x dx. Let's distribute this negative sign. So I end up that this is sine of 2x e to the x minus 2 cosine of 2x e to the x minus the integral of 4 times the sine of 2x e to the x dx. And what's this equal to? The integral of our original function, e to the x sine of 2x dx. Sorry, I ran out of space. And we see that we have minus 4 of these integrals on this side, and we have 1 of these integrals. These integrals are the exact same integral, right? Maybe I flip-flop the order of the e to the x. But if I add 4 of them to each side, it gives me that 5 times this crazy integral is equal to this value. Sine of 2x e to the x minus 2 cosine 2x e to the x. Uh-oh, my equal sign got a little messy, right? But then we're done, because now I divide both sides by 5, and that tells me what my integral is equal to. So I'm going to divide this by 5, and divide this by 5, and I end up with my final answer. So this was a messy by parts. I had to do by parts twice. Whoops. Get it from the sheet of paper. And we see that our final answer, that our integral, our original integral, is equal to, I'm going to factor out an e to the x also. It's equal to 1/5 e to the x times sine of 2x minus 2 cosine 2x. And so this, oh, plus c. So this is our final value. Finally, let's look at this tricky example. I'm busting out the really hard examples for this video because I think that you can work on doing easier ones on your own. It's more valuable to see some of the really tricky ones. What do we want to do here? Let's look at our checklist. This is not something that we see on our standard table of integrals. It's not quite one of these inverse trig things because the square root isn't in the entire denominator. It's also not something that I can do one of these trig substitutions with. Again, the square root isn't the entire thing. You might want to do it by something like partial fractions. These aren't polynomials in the top and the bottom. So I'm going to do a clever trick, and you could think of doing a number of tricks. Something that I might encourage you to try would be to multiply top and bottom by the conjugate. I actually didn't try that one out ahead of time, and it might be something that works. So this is an idea. I think that there are multiple ways to solve this. One idea might be to multiply both the top and bottom by x minus x times the square root of x. That clears up the denominator. It does mean that the numerator is still messy though. So instead of that, I'm going to do something clever, and I'm going to rewrite it or simplify it, and I'm going to rewrite the denominator by factoring out the square root x. So this integral, I'm going to first write x in a crazy way. So this x here is the same thing as square root x times square root x, right? Because if I multiply the square root of something by itself, then I get x back again. So this is plus x times the square root of x. This is sort of an intermediate step to show my algebra, but the real goal, the real reason why I wrote it like that is so that I can factor out a square root x. So I just rewrote this as this. Now, the next thing, why would I want to do that? Maybe I'm going to rewrite it one more time. So square root x is the same thing as x to the 1/2. And because it's in the denominator, this is x to the negative 1/2 multiplied by x to the 1/2 plus x all to the negative 1 dx. And this is where it makes sense to look for a u substitution. It's looking a little more like there is some sort of composition of function idea going on. And I'm going to pick sort of a clever version of u. I'm going to set u equal to x to the 1/2, because then my du is hiding right here. My du then becomes 1/2 x to the negative 1/2, or multiplying both sides by 2 du is, dx is equal to x to the negative 1/2 dx. So I have the x to the negative 1/2, and I have the dx. So I'm going to go ahead and start plugging in my u values. So this is equal to the integral of, I'm going to leave it messy. I'm going to write it, some of the pieces are going to have u's and some of the pieces are not. The dx and the x to the negative 1/2 becomes my du. This x to the 1/2 is u, but I'd still have this x here. How do I account for my x? So this is u plus x is actually just x to the 1/2 squared. So this is actually just u squared all to the negative 1 du. I'll do that scratch work over here to the side. But x is actually just equal to x to the 1/2 squared. And so that means that x is equal to u squared. That's what that substitution is. So finally, 1 over u plus u squared du plus u squared du. Notice that this is a ratio of polynomials. We have a polynomial that's really boring on top and a polynomial on bottom. There might be other ways to do this, but I'm going to do it by partial fractions. So the first step that I'm going to do is I'm going to actually factor this into u and u plus 1. Maybe I wrote that in a funny order, but this is the u squared and this is the u in the denominator. And I'm going to have to rewrite this in terms of fractions. So this fraction right here, 1 divided by u plus 1 times u, is going to have to be equal to a over u plus b over u plus 1. I need to figure out what a and b are going to be. You could do this formulaically, or you can see that on the left side we get u plus 1 divided by u times u plus 1 plus b times u divided by u times u plus 1. So I'm getting a common denominator because that's exactly what my original fraction was equal to. And I know that the numerators all have to be equal, so that's telling me that 1 has to be equal to a times u plus 1 plus b times u. I'm going to distribute and see that au plus a plus bu is equal to 1. Something that's not immediately obvious maybe is that this is the same thing as 1 plus 0 u. There are no u's on this left-hand side. So that means that au plus bu plus a is equal to this. The u terms all have to be equal, and the non-u terms have to be equal. So that's saying that 1 is equal to a. And that's also saying that 0 u's are equal to au plus bu. Or, we already know that a is equal to 1, that negative 1 is equal to b, because my coefficient here is 1, and I subtract it to that side, and I get 1 is equal to b divided by u. So these are our values for our partial fractions. Oh, sorry, I was off the board a little bit. And going back to our original fractions, that means that this integral up here is equal to the integral of a was the numerator of u, so this is 1 over u, plus what was b, negative 1, over u plus 1 du. And these are easy pieces to integrate. The integral of 1 over x is natural log of the absolute value of u, right, because it's a u and not an x, subtracting the natural log of the absolute value of u plus 1. In my head, this is actually a really basic w substitution, plus c. And then finally, I'm going to plug back in what my u was equal to in the original problem on the last page, slide 2 on the ground. Recall that u was equal to x to the 1/2. So this is the natural log of x to the 1/2 minus the natural log of x to the 1/2 plus 1 plus c. Whew, that's a messy one.